Hello everyone, my name is Neha and this is the 18th lecture on Introduction to Microcontrollers. In this lecture, we will be learning about analog to digital conversion. So let's get started. So basics of analog to digital conversion, where this A stands for analog and D stands for digital. Analog signal is any continuous signal and digital signal is any discrete signal. So we are going to see how we can convert a continuous signal into the discrete signal. So let's read here. Analog to digital converter can convert only electrical voltages into digital values. A transducer is needed to convert a non-electrical quantity into an electrical voltage. So you can see in this block diagram, which is basically the A to D conversion process. And the first block we have here is the transducer. And transducer is basically a sensor which sends a non-electrical quantity into the electrical quantity, or you can say it converts one form of energy into another form of energy. So these are different types of sensors you can use. For example, temperature, pressure sensor, light sensor, weight sensor, airflow, humidity. Um, so these are basically non-electrical quantities, I would say, and they have their specific sensors also, such as load cell, photocall, thermocouple. These are the transducer, and these are your non-electrical quantity which you are measuring. So you can say that this is your one form of energy which is being converted into another form of energy, and here the second form of energy is your voltage. So your temperature is being converted into the voltage, pressure is being converted into the voltage, and same with all these non-electrical quantity using different transducer based on what non-electrical quantity it is taking as an input. So that's the function of the transducer, which converts one form of energy into another, and here another form is our voltage, which is going into the signal conditioning circuits. This signal conditioning circuit, it is basically used to manipulate the analog signal in such a way that it meets the requirements in the next stage, where the next stage here is A to D converter. And the equipments which you can use to condition the circuit is, for example, like voltage or current limiter you can use, anti-aliasing filters you can use, which could be made up of op-amps, transistor, etc. And next we have analog to digital converter. There are many different circuits which have been invented in the past for A to D conversion, and they are as follows. For example, you can use parallel or flash analog to digital converter. You can use slope and double slope A to D converter. You can use sigma delta A to D converter. You can also use successive approximation A to D converter. Successive approximation is very popular method of converting an analog quantity into the digital quantity, or you can say analog signal into the digital signal. And then once you have the digital signal at the output of the A to D converter, you get this digital signal which you can use it in your computer. In our case, we will be sending this digital value into the microcontroller, and in microcontroller we have this microprocessor. So same in computer also, it also has microprocessor where you can send these digital values. In this quarter, you are doing a project named temperature indicator, and in that project, you will have to set you have to do the analog to digital conversion, and there are particular steps which you need to follow in when you write the program on the MP lab, and that's what we are going to learn in this lecture and the next lecture, how to set those values. Now moving on to the next. So we have this section has been taken from your data sheet. So you can refer to the 23.0 section, which talks about analog to digital converter. And it says analog to digital converter with computation allows conversion of an analog's input signal to a 10-bit binary representation of that signal. So far we have seen that we have been saving the values into 8-bit register so far, and then here we see we have 10-bit binary representation which we can save on microcontroller. So you might be thinking, where do we have this 10-bit register where we can save the values? So in this case, we when you use the analog to digital converter, you will be using two resistors together, which will form a 10-bit resistor. And those two resistors are these resistor ADRESH and ADRESL. So it says analog to digital result high and analog to digital result low. We'll learn about this more in next coming slides, but for now understand that you have this benefit in A to D conversion, that you can store the data in a 10-bit result, which will come out after the conversion can be stored in a 10-bit binary 10-bit register. So I'm gonna quickly read here the output of the starting from here. This device uses analog inputs which are multiplexed into a single sample and hold circuit. The output of the sample and hold is connected to the input of the converter. The converter generates a 10-bit binary result via successive approximation, where this successive approximation is one of the method I mentioned in last slide. In last slide, where I told you about 4 methods, and successive approximation is one of them, and very popular and mostly used in conversion. And in our particular case, in our microcontroller, this method has been used, and then it stores the conversion result into this A to D converter result registers. Okay, so these are the two pair of register which you will be using, and each pair has 8-bit register. Okay, so your 10-bit data can be stored in this pair of register, and we'll see that how the data is stored in the next coming slide. And additionally, the following features are provided within the analog to digital converter module. So these are the additional features which are important: 8-bit acquisition timer, hardware capacitive voltage divider, 8-bit pre-charge timer, adjustable sample and hold capacitor array, guard ring digital output drive, automatic repeat and sequencing, automated so under that we have automated double sample conversion for CVD, 2 sets of result resistors, auto conversion trigger, internal retrigger, computation features. We have averaging and low pass filter function, reference comparison, 2-level threshold comparison, and select table interrupts. So when you work on an extensive project, then you might be using some of these, and you will see like you will learn in that process when you make the project that how these particular things features can be used. Now let's see the application of analog to digital converter. As you know that in the modern world of growing technology, we are so much dependent on digital devices, and these digital devices, they operate on the digital signals, and not every quantity in the dish is available in the digital form. So in fact most of it are in analog form. So there we need to have a way to convert analog into the digital converter. or you can say A to D converter is used for converting those analog signals into the digital signals, and these are some of the application where they are used. In cell phones, to operate on the digital voice signal, these are used, and originally the voice is in that our voice is when it gets there is in the analog form, and which is converted through A to D converter before feeding to the cell phone transmitter. In images and videos captured using camera is stored in any digital device is also converted into digital form using analog to digital converter. And then we have music from cassettes is also converted into digital form such as CDs and thumb drives using analog to digital converter. And then we have digital oscilloscope. It also contains analog to digital converter for converting analog signal into the digital signal for display purposes and other different features. So you're very much familiar with digital oscilloscope application, and you know that you basically perform experiments and you see that result convert where the signal is converted from analog to digital. And then these can be used in air conditioner contains temperature sensors for maintaining the room temperature, and then that temperature is converted into the digital form using A to D converter so that onboard controller it can read and adjust the cooling effect. Now we're going to see the example of analog to digital converter. So this is an example of a your fuel indicator. You can see here this is the fuel indicator, and then this is a picture shown here which tells like how much is the fuel is and how using this how this float changes as the potentiometer here it changes based on the level of the fluid here. Okay, so in this application also we can use analog to digital converter. For example, if you see this fuel if you see this indicator, this indicates when the fuel is empty, and this indicates when the fuel is full, and in between we have divided into 4 different segments, and you can see at this segment it indicates 1/4, and then this indicates half full. Your fuel is half full, and then here when it reaches to here then it is 3/4, and then at here it is full. So you can say 4/4, which means 1 here. You can see how we have converted these digital this is a 2-bit here we have 2-bit we have used, and this analog to digital converter is going to tell us what fraction that we have in the tank right now. So if I said that I had a 2-bit number, then at least these 2 bits basically describe the value within the quantity of that fuel tank. So in this case here this particular represents an empty state, right? And this one represents your 1/4 state, and this represents your 3/4 state. This represents your half state, and this represents your 3/4 state. So you can see that how we have divided the range, and let's imagine if we have when the tank is full, at that time the voltage is 5 volts. I should have put it here the dimension. So this is your 5 volts. So when the tank is full, the voltage is 5 volts, and when the tank is empty, then the voltage is 0 volts. So this empty and full tank is based on the fuel level. If the fuel level is high, then the tank is full. If the fuel level is low, then that means then the tank is empty and fuel is low. So these are the two levels, high and low. 5 volts is high, 0 volts is low. And you see that we have divided into 4 different possibilities. This is 1, 2nd, 3rd, and 4th. And here is the same thing. So with this 4 bits possible combination, we get to know that in each range we have, if you divide it by 5 volts per 4 bits, we will get 1.25 volts per bit. So this much voltage is there per bits. So you can see that. So between 0, 0 and 0, 1, you will have from 0 to 1.25 volts per bits. And that's what we have. And between 0, 1 to 1, 0, you have 1.26 to 2.50. And between 1, 0 to 1, 1, you will have 2.56 to 3.77. And further here, you will have like till 5 volts. So you understand how it is increasing. So you got this thing, like 5 volts was our full tank voltage, and divided by different combination. And then you have this, and then this is per bits, this voltage per bits. And that's how we have found this. And then you keep on adding this, you will get this range, and here this range. Now here, if you want to increase the resolution, for example, if you want to have more voltage levels, like more divided, more possible combination, then you can use more than 2 bits. In this case, we have used only 2 bits, which has a 4 bits, like 4 possible combination. That's why we have 4 here. So it is actually not, I should have not written here as 4 bits. This is, I would say, is 4 bits possible combination we are having here. And that's why I have mentioned here. All right. So 5 volts per 4 possible combination of the bits. So you can have more combination if you want to increase the resolution. Okay, so now we're going to see some of the examples which and similar to those, you will be doing it in the project also. And like those are the base, and if you understand that base, it will be easy to do the same for your project in the temperature indicator. So let's see that. We have a 10-bit analog to digital converter. Reference voltage is given 5 volts, and V input voltage is 2.236 volts. In this case, we have to find the bit pattern. Okay, we want to convert analog to digital value, and we will see different steps how to do that in this process. So 10 bits means how many possible combination you are going to have. When you have 4 in this, when you have 2 bits, when you were using 2 bits, then in that case the possible combination you have is 2 to the power 4. Oops, it should be 2 to the power 2. Okay, so 2 to the power 2, how many combination you have? 4. So that's what you see here. So this is your 4 combination. Whereas in case of when you have 10 bits, then how many combination you are going to have? If you want to find out that, you will have to put 2 to the power 10, and that will give you number of combinations. Okay, so number of combination in that case are going to be 1024. These are the possible combination you can have in this 10-bit. And also remember that the microcontroller which you are using in that analog to digital converter, when you'll use, you can save the result in a 10-bit register. So you should know how many possible combination you can have. So you can have 1024 possible combination, and you know that this is the reference voltage. So compared to the previous example, we are going to find the volts per bits. So in this case, 5 volts divided by 1024 bits, and so after that you will get 4.88 millivolts per bits. Okay, for this pattern you got for this possible combination you got 4.88 millivolts per bits. So now we are given with input voltage, which is 2.236 volts. So you can compare this with the previous example. For example, if your fuel is set somewhere in between, then that would be your input voltage. So we have to find a bit pattern for that particular voltage. So the next step would be you divide this 4.88 millivolts per bit to this input voltage, and then you will get 458 point something something, and we are going to round it off to 459. Now the next step is to find the bit pattern. So that's how you find the bit pattern. These represents your bases. So for example, 2 to the power 0 is your 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 4 is 16, 2 to the power 5 is 32, 2 to the power 6 is 64, and 2 to the power 7 is 128, 2 to the power 8 is 256, 2 to the power 9 is 512. So you've got 459, and then just check for which is the highest number you have in these base values, which is lower than the number you got here. So we have 459, and if we see here 512 is greater than 459, so whatever is the lowest here, we're gonna take that. Okay, so and then you subtract this number from this 459, you get 203. And for this particular, when you use this, you'll put in that place as 1, and that's why you have 1. And then you see 203, and then again you check for which base, if the base next base here, is it greater or smaller than this number or not, can we subtract it or not. So we see that 203 is a bigger number compared to 128, so that's why we have subtracted here 203 by 128, and then whatever the result comes will be put over here, and then for this we set as 1, and that's why you have 1. Now we will look for next base. Next base is 64, and here our result is 75. 75 is bigger than 64, so you will basically subtract 64 from 75, and you'll get 11. So for this case also you'll get 1, that's why you have 1. And then you look for next base. So here result is 11, but the next base is 32, and 32 is greater than 11, so for this case you'll just put 0. 16 is also greater than 11, you'll put 0. 8 is smaller than 11, so you'll put 8 here. Minus 8, you'll get answer is 3. So and then you have 1 for this 8, that's why you have a 1. And then next base is 4, which is greater than 3, and that's why you have 0 here. And then next what you will have is you're going to have 2. You see here we have a 2, and 2 is smaller than 3, so you will basically subtract 2, and then so that's a subtraction sign, and then you will get 1 here. So you'll get 1 here, and then here also you'll get 1. Okay, and that's why you have 1 here. And then 1 minus 1 is your 0. So you'll do until you get 0, and then for this case you will get 1 here, and that's why you have this bit pattern. All right, so this is the way how you are going to convert whatever the round of number you got here into the bit pattern. Now the question is how you're going to store the value into the 10-bit register. So as I told you before that we'll be using two register name ADRESH, analog to digital result high, and in analog to digital result low. These two registers will be using to save the result, whatever the result you got in, you'll use these two registers and save the value in on that. We will see what these registers are and how they look like. So here, if you go to the 23.1.6 on your data sheet, then you will find this topic called result formatting. And I'm going to read this quickly. It says the 10-bit analog to digital conversion result can be supplied in two formats. First is your left justified, and the second one is called your right justified. So what does that mean? Either you can, so let's see, these are the two registers, ADRESH and ADRESL, and you can see that these are the 8-bit registers starting from 0 to 7, and this another register is also starting from 0 to 7. Okay, but we know that we can only save 10-bit result into this two register. So which means some of the bits will be left blank. And so there are two ways of saving the data. Either you can save in a left justified form or a right justified form. So for example, in this particular case, the first case, so this gray portion you see here shows your result has been stored in a right justified form because it is on the right side, and these other bits are going to be left blank. And in the second case, you see the result has been stored in the left side and the right side bits are left as it is, and this is called your left justified. And how do you tell the microcontroller to save the value in the left or right? For that, when you look at these register, you will see this bit AD so there is this ADFRMO which lies under AD-con 0, and this AD-con 0 you will be using to do the A to D conversion. And in that, when you make this ADFRMO as 0, then it means you want to put your result in a right justified form, and if you make this bit as 1, that means you want to put your result in a left justified form. For now, I would say just remember that this ADFRMO is what you will be using to decide whether you want to put your result in the right justified form or in the left justified form. And this bit this bit can be set in AD-con 0 register. So AD-con 0 register is another register which is used to set the analog to digital conversion. It is used in there, and I'll show you later in the slides like how it looks like. And it is again 8-bit register, and in that there is one bit which is named as ADFRMO. So this bit, when you make this bit as 0, then you make it as right justified, and when you make it as 1, then that means you are making it as left justified. Now reading here, software writes to the ADRES register pair are always right justified regardless of the selected format mode. Therefore, data read after writing to ADRES when ADRFMO 0 will be shifted left 6 places. And that's what you see here. When ADFRM0 MO is 0, then the data is moved to the left, and when it is 1, to the right. So for now, just understand that two register pair ADRESL and ADRESH are used for result placement from analog to digital conversion when you do that. And then to set right or left justified, you use ADFRM0 MO bit which lies in the AD-con 0 register, and you make it 0 and 1 to make either left justified or right justified. Now we are going to see the previous example which we saw, and we are going to see how we will be putting up the result we got in these two registers. So this thing we already covered. This was the round off, and we did the math to find out the bit pattern. And then now we are going to see, so we will be storing the values, or we'll be storing the result in the right justified form. So this is the right justified form. This is ADRESH, ADRESL register pair, and this is my result, and that's how I have shown here. Okay. Now moving on to the next example. Now here we have 8-bit A to D converter. Reference is given 3.3. Input is given 0.625 volts. And we have to find the bit pattern. So 10-bit is 2 to the power 8, which means 256, and then divided by this number of bits divided by 3.3 reference voltage, we will get 12.8 millivolts per bit. And then we have input voltage is this, so we divide this value from the input voltage, and we'll get 48.8 and round 0.8 something something. When you round off, you'll get 49. And then the same process you will do. You'll see which base is smaller. So definitely our range is maximum is 256. Okay, but based on our input, we got this round off, and smaller than 49 is only 32 here, and then all these bases which are on the left. So 49 minus 32 is 17, and then your bit will be set as 1 here. 16 is smaller than 17, that's why you have 16 here. Bit is set as 1, and then 8, and then remainder here, the result is here is 1, and 8 is greater than 1, so that's why you have 0 here. You cannot subtract that. And then 4 is also greater, so 0 here. 2 is also greater, 0 here. 1 is you can use and you can subtract, and you'll get 0. So you'll do it until you get the 0. So for this case, you will set it at 1. So this is your result, 110001. And the result is stored in a left justified form. So in this way, you will store the result. Now next example we have is for 12-bit A to D converter. Reference voltage is 4 volts, input voltage is 3.3 volts. Bit pattern we have to find. We know that in the microcontroller which you are using can store only 10-bit data, but this is just an example I am taking. So let's see, 12-bit, which means 2 to the power 12. We're going to have different combination around 4096, and that will be divided by this reference voltage, and we will get 976.5 microvolts per bits, and this voltage per bit we are going to divide it from 3.3 volts, and we will get 33779. So this is the math you'll do, and that's how you find the bit pattern. If you don't understand, then I'll just pause the video and see how I have subtracted these base values, and then I've got this bit pattern here. So after 2048, whatever you have is going to be bigger than 3379. That's why I have used 2048 here, and then you'll get, when you do that, subtract, you'll get 1 here, and then so on. You will get this bit pattern. And then the result is stored in the right justified form. So this is the result, 1101 00110011. So the result has been stored in the right justified form. Now next, in this example, We have 4-bit A to D converter. Reference voltage is 1 volts. Input voltage is 0.5 volts. We have to find the bit pattern. So this one is pretty simple. So 2 to the power 4, we are going to get 16 different combinations. And 1 volt divided by 16 bits, we are going to get 0.0625 volts per bits. And this divided by this input voltage, we will get around 8, which means this is our bit pattern. Okay, now just imagine if you are writing a code and if 8 is your target value, then how you're going to write the code. So let's say in the temperature indicator project, you want to achieve 75 degree centigrade, and let's imagine that 75 degrees centigrade is equals to 8, and this is our target. So, and you have to find out the temperature above and below also, so that you have a particular range. Similarly here, 8 is our target, and then upper threshold is 9 and lower threshold is 7. And then for 9 and 7, you can calculate, if you put here 9, then you can calculate the input voltage in that case. So input voltage in that case is going to be 0.56. Obviously it's going to be slightly bigger than this 8, because 8 is our target and 9 is above the target, so input voltage is going to be higher. And if it is below the target, then input voltage is going to be slightly lower than the target voltage, so it is 0.437, and that's how you represent in the binary. Now you know how you can calculate these two values through this formula, just putting here 9 and 7, and you can get this input voltage. Now, how we can write the program in the microcontroller in such a way that it only indicates the value when it is at target, and it also indicates like if it is above target or below target, at a below target or at a above target. Okay, and a target value. So for that, let's see here. When it is at target, so we can use this logic. When it is at target, then subtract 8 minus 8, because that's the bit pattern you will get, and then you will set some reference value, which is this bit pattern you will set, and you subtract from that, and in that case you're going to get the 0 number, right? And as I said in the last lecture, I guess, you can use a status register. You might have used it for button input, and in this particular example also you'll be using status register, in which you have the carry and this Z bit, which these two you can use to indicate your results. So in this case, when you subtract target minus reference, then you get 0. In that case, the carry is going to be 0. Since the answer is 0, the Z bit will be affected, which is going to be 1. And then at above target, what you are going to do, you get above target. At above target, you have this 9 bit pattern, and then 9 minus the reference, which is 8. So you'll set a reference. Okay, so 9 minus 8 reference, you'll get a positive number. In that case, you're going to have carry bit will be affected, so it's going to be 1. But since the arithmetic operation output is non-zero, so in that case your 0 bit is not going to be affected, so it's going to be 0. Third case, when it is below target, then you're going to subtract it by the reference value, and in that case you're going to get a negative number with borrow, and in this case the carry is going to be 0, and again the operation is the result is non-zero, so your Z bit is going to be 0 in this case. If you have any confusion how you got Z is equals to 0, Z is equals to 1, then I would request you to read the status register, and I think we'll be covering in this lecture also in the coming next slide. So So yeah, this is your status register which I was talking about, and this is the carry bit, and this is the Z bit which we use. And I think I covered in the last lecture uh, what will happen when your Z is going to be 1 and when your Z is going to be 0, and same with here. You can look it up in register 3-1 in your datasheet, and if you want to reread, you can go through this register, and you'll get to know how what all these things mean. Now this is the code for target range, and this is how you're going to use the code, and the similar code, but you can use different labels for your temperature. Okay, temperature indicator project. So let's see here. At target, we know this thing, subtracting 8 minus reference value, which is 8, a 0 number, and status carry 0, and Z bit is 1. So first thing we are going to do is to move the literal number to the working register, and 0, 8 hexadecimal number we are moving, and then subtracting the working register from the file register, and ADRESL. You remember we had these two register pair, ADRESL and ADRESH. So those two register pair you use to store your result. So let's say you have some input, some result already stored here, and you want to compare it with the reference value. So yeah, you have, let's say you have some value in this register, which is stored here, and this one indicates you want to store the value in the file register. Okay, so you do that, subtract W with F. F is your this file register, W is here, 08 will be subtracted from here, and then next you are going to do is the bit test F, skip if clear. Okay, status register you are using, you are checking the bit Z bit. Okay, you are checking the Z bit whether Z bit is 1 or 0. And what it's going to do, it's going to do the bit test for this Z bit, and it's going to skip the next instruction, which is go to temperature, target temperature, if the Z bit is 0. Okay, so bit test F, skip if clear. If Z is equals to 0, then it is going to skip this instruction and will go to this one. So Z is equals to 0 is in two condition. You see that Z is equals to 0 and Z is equals to 0 is in these two condition, when you are above target and when you are below target. Okay, so let's say our bit Z bit is 0. Okay, so if Z bit is 0, then it's going to skip this step and it will go here, and then it is going to do bit test F, skip if set. Okay, so it is now here, this is going to this is checking the carry bit, because the first logic we used whether Z is equals to 1 or 0. So if Z is equals to 0, then definitely we know that either we are above target or we are below target. Okay, now how to differentiate between these two, like whether you are above target or below target, that you can do by checking the carry bit. You can see here the carry bit is 1 and carry bit is here 0. So that's what it is checking here. Bit test F, skip if set. So if your carry bit is set, which means carry bit is 1, then this is going to skip this step and go to this step, and that's what it mentioned here. If carry bit is 1, then that means you're above target, and that's what it says here. If your bit test F, skip if set, if it is set, then this will go to this above target. So carry bit is 1, then it is above target, and if it is not 1, which means if it is 0, which is this case, then it is going to go here below target. So you understand my point, like it is first here it is doing a bit test for Z whether it is 0 or 1. If it is 0, then it is going to check the carry bit. Okay, so two easy steps. First, checking the Z bit whether it is 0 and 1. If it is 0, then the second step is it will check the carry bit whether carry bit is 0 and 1. If it is 1, that means you are above target. If it is 0, that means you are below target. And then here, if the carry bit is 1, then it is not going to skip this step. It will go to this step, which is go to target temperature. Now, what are these? Target temperature, below target, above target. So these, you have to put some code here. So target temperature code will go here, below target temperature code will go here, above target temperature will go here. And that's where you have to put the logic, like how you are going to create a code for these three. But then this is the main logic, how it is going to decide whether it is at a target temperature or below or above. All right. Now let's move on to PIC 18, A to D converter. And you already know that it is a 10-bit A to D converter, and for this particular project in which you have to indicate the temperature, different temperature. For that project, you will be using all these resistors. ADRESH, ADRESL, you'll be using ADCon 0, ADCon 1, and very important and critical resistor, which is ADPCH resistor, you'll be using. So these first two resistors, these are result high resistor, result low resistor, which you'll be using in pair, and these are the two control resistor, ADCon 0, ADCon 1, and then this ADPCH resistor determines which channel is connected to the sample and hold circuit. So this sample and hold circuit is a part of A to D converter. If you see the block diagram of A to D converter, then you will get to know that you will see that this circuit is present, is there. Now through this, so all these resistors, they lie in the banks 1, and that's what I've shown here. You see that at this particular address, hexadecimal address 8C, you have this ADRESL. At 8D you have ADRESH. At 93 hexadecimal you have ADCon 0, 94 you have ADCon 1, and then at 9E you have ADPCH. Alright, so these are the resistors which are primary for A to D converter, and you will be using all of them. The contents of these resistors vary with the PIC 18 members, so it may be possible that if you're using the high version of PIC 18, then maybe these their name might be a little bit different. Okay, now and then always remember the result will be stored in 10-bit A to D converter for PIC 18. Now let's first see ADCon 0. I won't be covering up ADRESH and ADRESL because those you have already seen in the previous slides. So I'll just directly move on to ADCon 0. So here ADCon 0 is here, and this is the 8-bit resistor you can see. I'll quickly read here. Starting a conversion to enable the ADC module, the ADCon bit of the ADCon 0 resistor must be set to 1. Conversion may be started by any of the following software: setting the ADGO bit of ADCon 0 to 1, an external trigger, a continuous mode retrigger. So as I told you in the initial slides of this lecture, that you will be using ADFRMO, this bit. If you make it 0 and 1, that means you are making the results stored either in right justified or left justified, and that's what it says here. So 1 ADFRM01, that means you're storing the data in the right justified form. If it is 0, then in the left justified form. And AD on is A to D converter enable bit. So if it is 1, then ADC is enable, and if it is 0, then it is disable. So when you are using this ADCon 0, then you have to enable this bit. And then you have ADGO. ADGO is here, which basically the ADC conversion status bit, and if it is 1, then ADC conversion cycle is in process. And setting this bit starts an ADC conversion cycle. The bit is cleared by hardware as determined by the ADCONT bit. And if it is 0, then ADC conversion is completed and not in process. Okay. So this register you will be using, and then you will be using ADCON1. And these are the different register under this 8-bit control register. So this ADPOL, ADPEN, and ADGPOL, it has some meaning which you can read here. And I will be telling you how to set this bit. Let's little bit read here. ADD POL, which is a pre-charge polarity bit. So action during first pre-charge state. External select analog input output pin. Internal analog to digital sampling capacitor. If it is 1, that means shorted to VDD, and capacitor hold shorted to VSS. If it is 0, then shorted to VSS, and C hold shorted to VDD. And then if your AD pin, which is A to D inverter pre-charge enable bit, if it is 1, then the pre-charge and guard signal in the second conversion cycle are opposite polarity of the first cycle. And if it is 0, then both conversion cycle use the pre-charge and guards specified by the ADPOL and ADGPOL. And then these are ADGPOL guard ring polarity selection bit, and this is ADSEN. So I'll let you know what are the bits you need to set, and if you want to get in detail, you can read this particular control register from the data sheet. And then another important is your A to D conversion configuration. So you can look it up in your data sheet 23.1. When configuring and using the ADC, the following functions must be considered. Port configuration, channel selection is very, very important. ADC voltage reference selection is important. ADC conversion clock source, interrupt control, result formatting, conversion trigger selection, ADC acquisition time, pre-charge time, additional sample and hold capacitor, single double sample conversion, guard ring outputs. And here you see this is important, very important here. You can read all of these, but then okay, let me read this and then I'll directly jump into this one. So ADC can use to convert both analog and digital signals. When converting analog signals, the input output pin should be configured for analog by setting the associated trace and ancel bits. So you already know this thing. And now jumping on to this one. This is ADPCH, register determines which channel is connected to the sample and hold circuit. So we'll be using this. And now let's move on. So to this ADPCH, so this register will be using for channel selection. And this is the 8-bit register. And you can see from here, if you are giving this value from in your program, then that means you're making it fixed voltage reference. If you're giving this value or sending this value into this register, that means you are making it as DAC1 input. If you're using this, then temperature indicator. If you're using this, AVSS, this for reserved, and then so on. So you can see, so all of these are different. You can send this binary number into the register, and corresponding to that these pins will be affected. So A and A0, where this A is basically for your port A. So if you choose this one, that means port A, the bit at the 0 bit at port A will be affected, and this is for port A, 1 bit will be affected, and from 0 to 7 is your port A, and from 0 and A and B 0 to A and B 7 is from 0 to 7, and then from this is for port B, and this is for port C, A and C 0 to A and C 7, port C, and then port D, A and D 0 to A and D 7, port D, and this is for port E, A and E 0 to A and E 2. So we'll see the example like how we can use this in the next lecture. And the last piece in this lecture is this A to D conversion, and you can find this example in the data sheet 23-1. So this example which has been shown here is an old example. If you try to use this, then you'll have to do some modifications. For example, in this one, it doesn't have this resistor which we saw here, ADPCH. So channel selector resistor is missing in this one. So if you try to run this, then this is not going to configure your A to D conversion. It's not going to do that. Okay, so some change we have to do, but it's nice to go through this and try to understand what is happening in this code. And we'll talk about we'll be using some of this code, and then some new code also for channel selection, and then we will be doing the A to D conversion, and I'll be showing you the example in the next lecture. So spend some time on this example, and I'll see you in the next lecture. So this is it for now. Thank you so much for watching.